So Tuesday this week we start talking about normal distribution. Okay, I will first of all quickly go over what we have discussed so far. Okay, so for normal distribution, this is x follow n. N is for normal, mu is the mean value, and sigma square. Okay, which is the variance. Okay, for any normal distribution, we follow 68, 95, 99.7% rule. Okay, so which means 68% of population fall within mu plus minus 1 sigma. Okay, 95% within mu plus minus 2 sigma, and 99.7% within mu plus minus 3 sigma. Okay, so the shape of all normal distribution will be the same. And then because of that, we normalize normal distribution. Okay, we call that standard normal distribution. Okay, by calculate the z-score. Okay, so z-score, z-value is equal to x minus mu divided by sigma. Okay, so z-score means the number of standard deviation sigma line from the mean value. So for how far away the x from the mean value. Okay, so that is z-score. And then we show the standard normal distribution. Okay, the mean value is 0, standard deviation is 1. Okay, and the total areas under the normal curve is 1. Okay, 100%. By the way, that's true for all type of probability density function. Okay, and z-score could be positive or negative. Okay, to the left is negative, to the right of the center positive. And then we try to calculate the z-value. Okay, so z-value using this equation x minus mean value mu divided by sigma, standard deviation. Okay, so we can calculate the z-score. After that, we can use table 8.2, which is called z-table from our textbook to find out the probability. Okay. Also, we discuss, if we know the z-score, we can back calculate the x value. Again, use the same equation. All right. Finding areas under a normal curve is to find the probability. Okay. But for normal distribution, do the integration is very, very complicated. And that's the reason we use z-table instead of integration to find out the probability. Okay. And then we start to discuss how to use the z-table. Okay. That's from page 818 on our textbook. It is table 8.2. Before we do that, we need to convert the normal distribution into a standard normal distribution. Okay. Basically, we calculate the z-value using the equation we just discussed. Okay. Also, for that curve, pay attention. The table shows the area or the probability in the left-hand tail of the curve. Like we can see from here is the blue shaded area. So remember that. Other areas can be calculated by subtracting or using the fact that the total areas under the curve is 1. Okay. And then we start doing some examples. Okay, how to use the z-table. Okay, here the z-value. Okay, 1.36. So for the first column of the z-table, okay, it is 1.3. Sec is the first row in the table, so 0.06. So 1.36 is here, 0.9131. Okay, so which tells us a random chosen value for z-score less than 1.36, the probability is 91.312%. 1%. Okay. Also, we can calculate for probability less than certain z value, larger than certain z value. For larger than, we use 100% minus the value we found from z table. Okay. Or we can find out any range, for example, from minus 1.2 to 1.36. So we get two values. The first value 0.9131 is from for z value of 1.36 minus the probability from z table corresponding to z value of minus 1.2, which is 0.1151. Okay, so 0.798 is the probability between z value of minus 1.2 to positive 1.36. We also discussed how to work backwards. Basically, okay, if we know the probability, how we can find out the z value. Okay, if we know the probability, we just find out, for example, here, closest to 0.25, we find the value closest to 0.25. Sometimes we can take the average of two values. For example, in this case, okay, then we find out the z-score. So that's called work backwards. Okay. If it's asking the value of z has area of 0.05 to the right, then we use 1 minus 0.05, which is 0.95. So that's the value we need to look for in the z table. Okay, so working backwards.
Professor, I have a question.
Yes.
In table A2 on page 18, is that like a standard table whenever you're using this standard normal distribution? Is this like a something that we can find in other places?
Yeah, it's always the same. For all the normal distribution, you use that table. Okay, you use that.
I see.
Okay, all right. Okay.
Thank you.
Okay, you're welcome. I think we stopped here last time. Okay. All right, so let's slow down. Okay, talk about more practice. Okay. So find the area under normal curve to the left of z 0.47. Okay, so let's look at the z table together. Okay, first of all, let me okay, all right. Okay, here is z table. Okay, for table 8.2, the z table, the z value again could be negative. Okay, as we can see from here, or could be positive. Okay, z value of 0.47. We found out where is 0.47. Okay, so here 0.47 is here. Okay, right. So which is corresponding to z value of 0.4. The next digit is 0.07 here. So that's why 0.47 is here. Okay, so 0.6808. So the probability, it's very hard to write on iPad, especially when it is vertical. Okay, so let me put it down. Z value less than 47 is this much. Okay, so from here, 6808. Okay, find the area under the curve to the right of z 1.38. Okay, so first of all, let's find out the value 1.38 for z-score. So 1.3 is here, right? 1.38 is here, 0.08. It is here. You can see here. So 0.19162. Okay, so remember for the z table, it tells us the left-hand tail. Okay, so that's pz less than 1.38 is 9162. So the question is asking curve to the right of z. Okay, so right of z, basically we use 1 minus that value. Okay, so don't forget that part. Okay, so which will be 0.0. Oh, okay, 0.0. Okay. Right. Next, find the area under the normal curve between two values, 0.71 and 1.28. Okay, so between two values, okay, so that's the z. So 0.71, 1.28. Okay, so to find out these areas, okay, first of all, we need to find the value corresponding to z less than 0.71. Okay, so p less than 0.71. Okay, 0.7 is here, 0.71 is here. Okay, good. 0.7611. So P Z less than 7Y is this much, 7611. Okay, right. So that is this area. Okay. Then we found out P Z less than 1.28. Okay, 1.28. So 1.28 is here, 1.2 is here, 1.28 is here. Oh, I cannot highlight. Okay, 0.8997. Right? Okay. 0.8997. Right. So where is 0.997? That is how I can show here is this area to the left-hand tail of 1.28. Okay, so the areas in between 0.71 and 1.28 is therefore 0.8997 minus 0.7611. So P between 71 and 1.28 will be 8997 minus 7611. Okay. 1386. Okay, so basically three kind of situations: less than certain value, larger than certain value, or in between two values. Okay. So normal distribution is very important. How to use Z table or table 8.2 is very, very important, not only for this chapter, but also for chapter 5 and 6. Basically, remaining of this class, we'll use table quite a lot. Okay. The good thing is it's not very difficult to follow, right? So only several tricks. Okay, it's not very hard to to understand. Next, z-score corresponding to 75th percentile. Okay, so 75th percentile. Then we need to find out anywhere corresponding to 0.7500. Okay, it is around here. So for z-score of 0.67, it is 0.7686. The next one, 0.68, will be 7517. Okay, so we know 75th percentile will be somewhere between 0.67 and 0.68. Okay, so we can use the average of these two values. 67 plus 68 divided by 2. Okay, 75. So we found the closest value corresponding to what the question is asking. In our case, 75th percentile. Okay, this is again working backwards. Tells us the probability asking for the z-score or even the x value. Okay, the idea is the same. All right. Estimating parameters. So here tells us if x1 to xn are random sample from a normal distribution, okay, with a mean value of mu and the variance of sigma square. Okay. We can estimate the mean value using sample mean. Okay. For the sample mean, the uncertainty will be sigma over square root of n. Okay, so that's the same for almost any type of sample mean. Okay, as we discussed in the Poisson distribution, for example. So we can see if we increase the sample size n, okay, the sample mean, the uncertainty for sample mean will become smaller. Okay, so increase n, this value becomes smaller. So uncertainty becomes smaller. Okay, but the mean value is unbiased. In other words, the bias of the mean value is 0. Okay, or we call that unbiased.
I'm sorry. You're saying the biased value of the mean equals 0?
It is unbiased. So bias is difference between a mean value and true value. Okay, so
okay.
Yeah, just remember the mean value is unbiased. All right. Okay. Here, sorry, a lot of error here. Okay. So this is a linear function of normal random variables. Okay. I don't know why it's showed here. If x follow normal distribution, okay, and a and b are constant, a not equal to 0, then ax plus b will follow another normal distribution with a mean value of a mu plus b. The variance actually will be a to the power of 2, a squared, sigma squared. Okay. So actually the error to the top means a superscript. Okay. And error downwards means subscript. Yes. Yeah. Sorry about the display error. Okay. More general, okay, if x1, x2, xn are independent, normally distributed, okay, they have different mean value, mu1, mu2, and different variance. Okay, so that is all right. Okay, so sigma 1 square for x1, sigma 2 square, so on. sigma n squared. Okay. And the C value are constant. And then C1 plus X1, C2 plus X2 will follow normal distribution. Okay. So let me just write it down. So that's C1 mu1 plus C2 mu2 plus Cn mu n. Okay, so that's the mean value for the new normal distribution. For the variance is C1 squared, sigma 1 squared plus C2 squared, sigma 2 squared plus Cn squared, sigma n squared. Okay, so that's called a linear function of normal random variables. Okay, so here is the simple example. So measure the temperature of solution in degree Celsius. Okay. The measurement is denoted C for Celsius. That value temperature is normally distributed with mean value of 40 degrees and a standard deviation of 1. Okay. If we convert degree Celsius to Fahrenheit, okay, we use that equation. Fahrenheit is equal to 1.8 C is for Celsius plus 32. Okay, what is distribution of F? So that's the linear function of normal distribution. Because C is normally distributed and F is a linear function of C. Okay, so both C and F are normally distributed. Okay. So the mean value for C is 40. The variance for Celsius is 1. Okay, 40 and 1. Okay. So the mean value for Fahrenheit will be 1.8 times 40 plus 32. Okay. That is 104. And the variance is 1.8 squared times 1. Okay, so 3.24. Okay, so that's the linear function. So the mean value and the variance, okay, A squared. So F will follow normal distribution with a mean value of 104, variance of 3.24. Okay. Distribution of function of normal. Okay, so if x1 to xn are independent and are normally distributed, okay, with a mean value of mu and variance of sigma squared, okay, then this is the mean value of x1 to xn. Okay, so the mean of x1 to xn follow a normal distribution of mu. Okay, mu doesn't change. The variance become this sigma squared over n. Okay, so again, we can see if we increase the sample size n, the variance will become smaller, but the mean value does not change. Okay. The next one, we have two normally distributed functions, x and y. So they follow different parameters, but both normal distributions. Okay. So x follow n mu x sigma x squared. Y follow n mu y sigma y squared. Then pay attention to this. Okay. So x plus y follow another normal distribution. Okay. So sigma mu x plus mu y is the new mu. Sigma x squared plus sigma y squared is the new variance. Okay, but for x minus y, the mean value, will be mu x minus mu y. Okay. However, pay attention to this. The new variance still will be plus. Okay, so that's not a typo. So the mean value still be sigma x squared plus sigma y squared. Okay. Okay. All right. Okay. Questions so far?
I'm still a little confused, even though you explained it to us. Are we gonna have an example where we can see how this?
I just suggest you to maybe look at the video from the previous lectures. You may miss that.
Okay.
Yeah. So after that, we can set up an individual time, just you and me. Okay. So you have any questions, I'm very glad to help. Okay.
Thank you.
Okay. Thank you. So finding property for the general normal random variables. Okay. Again, this is to find areas for the normal random variables x, okay, with a mean of mu, standard deviation of sigma. So first thing we need to do is we standardize, or we can call that rescale. Okay, or we call that we calculate the z-score. Okay, same idea. Okay, we calculate z-score first, then we use the table 8.2 to find out the probability. Okay, so like in this example, we want, so x follow normal distribution of mu of 5 sigma 2. Okay, so we found that the probability for x larger than 7. Okay, so first of all, we found out the z-score corresponding to x equal to 7 for that normal distribution. So z-score is equal to x minus mu divided by sigma. Okay, so x is 7, mu is 5, sigma is 2. Okay, so we calculate z-score is equal to 1. Okay, so that tells us x is 1 standard deviation away from the mean value. So 1 standard deviation away from the mean value. Okay, so because z-score we calculate equal to 1. Okay, so 1 standard deviation away, actually in this case larger than the mean value. Okay, if z-score, for example, is minus 1, this is 1 standard deviation smaller than the mean, so which will be here. Okay, minus 1. Okay, so we found out px larger than 7. So larger than 7, this is on the right hand tail of the z. Okay, but remember from the table 8.2, okay, it only tells us the left hand tail. So let's find out where z-score of 1. Okay, so z-score of 1, 1.0 is here, 0.8413. Okay, so that is the left hand tail. Again, left hand tail. Okay, the green blue area. So we need to use 1 minus 0.8413. Okay, I hope that does make sense to you. Okay, so the probability for x larger than 7 or for z-score larger than 1 is 15.87%. Okay, so let's continue to do some more practice. So no need to rush. I think we are kind of ahead of schedule. By the way, before I forget, for the first homework, I know the due date is today, but some of you email me, see if it's possible to extend the due date. So I did extend the due date to Monday next week. So March 1st by the end of day. Okay. Yeah, you have some more time to work on it. And also, some of you ask me about the time for the quiz and the midterm. Okay. First of all, the midterm will cover from chapter 1 to 4, which is will finish by next week. Okay. So, but the first quiz will be sometime in late part of March, around March 20 something. So after the spring break will be our first quiz. Okay. And then the first quiz will serve as a practice for our midterm. So our midterm will be in early to middle April, around April 10th, plus minus. Okay, so that's the general schedule for our quiz and midterm. Another example using Z table. So the weight of package of ground beef normally distributed. Okay. So mean 1 pound, standard deviation 0.1 pound. Okay. Asking probability and randomly select package weight between 0.8 to 0.85 pounds. Okay, so we know probably right now already. So we need to transfer X into Z score. Okay, then we using table 8.2. Okay. Mean value 1, sigma 0.1. Z score X minus mu over sigma. Okay, so question asked between 0.8 to 0.85. For 0.8, the Z score, so 0.8 minus mu 1, Z score 0.1. Okay. So this is for 0.8. Okay. Z score is equal to this. So turned out Z score is minus 2. Okay. For X of 0.85, okay, the Z value will be 0.85 1 over 0.1. Okay, so that is minus 1.5. Okay, so that tells us, again, Z-score means how many standard deviation away from the middle, from the mean value. If it's negative, it is on the left side. If it's positive, that's on the right side of mean. Okay, so for X equal to 0.8, that is minus 0.2. Okay, so 2 standard deviations smaller than the mean value. Okay. So first of all, we calculate, we can find out this area. Okay, so this area is corresponding to the probability in the table 8.2 for Z-score of minus 2. Okay, so let's look at the Z table now. Minus 2 is here. See here? So 0.0228. Okay. So that is these areas, 0.00228. Okay. Then we look at the probability for Z-score of minus 1.5. Okay. So minus 1.5 is here. Okay. So 0.0668. So that area is where is here. Okay, let me just draw. Another normal curve, just show you clear. Okay, so this is minus 1.5. So this is this area, which is equal to 0.0668. Okay, so that's why the answer used 0.0668 minus 0.228. Okay, so because the question is asking the red area here. Okay. Questions about this? Okay, this is very important and also very, I think, very basic. You have to understand how to use the z-table to calculate depending on what the question is asking. Okay. Question. All right. So
yeah. So hold on a second. So the probability P equals 0.0440.
yes, 0.0.
It's P, right? P equals.
Yeah. So next part of the question is working backwards. Okay, so what is the weight of package such that only 1% of all package exceed this weight? So we know the probability. Okay, only 1% exceed that weight. Okay, so that's 99th percentile. Then asking for the x value. Okay, the question asking for the x, which is the weight of the beef. Okay, so z-score is equal to x minus mean, which is 1, divided by sigma, which is 0.1. Okay, and that is probability is 0.01. Okay, so 1% exceed all package. Okay, but this is the right-hand tail. The right-hand tail, remember the table 8.2 is left-hand tail. So we need to find out the probability of 1 minus 0.01. Okay, which is 99%, 0.99. Okay, so we go to the table 8.2, find out what is z-score corresponding to p-value, the probability of 99%. So where it is here. So 0.9901. Okay, close enough. Okay, so you can just use the z-score corresponding to 0.9901, which is 0.233. Okay, 0.233. Okay, so that is z-score 2.33. Then using this equation, we figure out what is the weight of the meat. So 1.233 pounds. So for meat of 1.233 pounds, only 1% of the chance and random chosen package is heavier than that. Okay. Okay, so that's the end for normal distribution. In this chapter, we have some more distribution, but I decided not discuss in this class. Okay, so then we directly jump to section 4.10 and 4.11. Okay, so 4.10.
Excuse me, Professor. Excuse me, Professor, before you leave that last example, just to clarify, the question mark value is 0.99, right? The question mark in the example?
The question mark is the weight of the beef, is X.
Okay.
Yeah, 0.99.
I was just wondering how.
0.99 is P. Okay, P.
Okay. Oh, P equals 0.99. Okay.
Yes. Yeah. Okay.
Thank
P,
you.
Yeah. Okay. Yeah.
Thank you.
Okay. All right. So let's continue. Don't think we need a table for now. Let me just get rid of the table. Okay, we are here. So probability plot. So what does that mean? Put my iPad in vertical. So let's just read together. So scientists, engineers often work with data that can be thought of as a random sample from some kind of population. For example, normal distribution, or Poisson distribution, or binomial distribution. Okay, but it's not always we know what type of distribution that experiment follows. Sometimes we do know. Okay, for example, if we toss the coin 10 times, okay, you know it is follow a binomial distribution, because based on the procedure of the experiment, we know already it will follow a binomial distribution. Okay, but not always. Sometimes we do not know. Okay, so how we can determine what type of distribution that experimental follows. Okay, so that's this section 4.10 probability plots tells us. So more often than not, the only way to determine the appropriate distribution is to examine the sample, okay, to find a probability distribution that fits. Okay, for example, if we guess that sample, we get 10 values. Okay, we want to check if that sample follow a normal distribution. So how we can determine that? So we can use a so-called probability plots to determine appropriate distribution. So suppose we have a random sample, x1, x2, xn. Okay. First of all, we need to arrange the data from small to large, ascending order. Okay. And then we assign evenly spaced value between 0 to 1 to each xi. Okay, for example, we assign value of I minus 0.5 over n to xi. Okay, in a moment, I'm going to show you an example. Okay, then let's just read the second paragraph. Distribution that we are comparing to x2 should have a mean value and a variance that match the sample mean and variance. Okay, so what we need to do is we plot xi and f, xi. So f is the function, for example, a normal distribution. Then if this plot resembles CDF, CDF is the cumulative distribution function, okay, that we are interested in. Okay. For example, we plot CDF for normal distribution, and we see if the data points from the sample fit in that curve. Okay. The closer the data points fit in the curve, then we are more confident the experiment will follow that distribution. Okay. Let me just give you an example. Okay. How to do this? So let's see if we have 5 data points. Okay. And what we need to do is we arrange from small to large. Okay. N is 5. So I 1, 2, 3, 4, 5. Okay. And let's see if we have the sample results for xi. The first one is 3.01. Second one, 3.35. Third one, 4.79. Okay, so this is 5 sample points. Okay, from our experiment. For example, we crash the concrete cylinder. That's the strength we get. We want to know what type of distribution that result follows. Okay, so first of all, we do this. Okay, we calculate I minus 0.5 divided by 5. 5 is n. Okay, so that value is 0.1. 3.9. Okay, so that reflects the position of xi in the order sample. Okay, so that's one way to do that. We can also use software. Okay, so software can calculate that value. Okay, and then calculate the quartile corresponding to that number from the distribution of interest. If we suspect it follow a normal distribution, we use normal distribution. Okay, and then if you plot each xi and qi, and we can check if the plot follow a straight line. Okay, if that's the case, we can conclude the sample probably come from the distribution we guessed. Okay. For example, from the previous 5 samples, we calculate the mean value. The mean value we calculate from here is 5. Okay, and the sample standard deviation we can also calculate. Let's say it's 2. Okay, then we can check if the sample value follow a normal distribution. Okay, for normal distribution with a mean value of 5 and the variance of 2 squared. Okay. So here shows the cumulative distribution function, CDF, okay, for a normal distribution. Okay, and also it plot the data points. Okay, so xi and qi. Okay, if xi follow a normal distribution, okay, then the plot should close to the line. The dots should close to this CDF line. Okay, so in this case, the 5 dot is pretty much close to the CDF for a normal distribution, okay, of 5, 2 squared. Okay, then we can conclude for this sample of 5, it follow a normal distribution. Okay. We can also use this. Okay, this is for the XL, XXL is XI. Okay, for the YXL is QI. Okay, so how to calculate the QI? Let me show you. Because here, okay, for example, for xi of 3.01, okay, we calculate I minus 0.5 over 5, that is 0.1. Okay, then we suspect the sample follow this normal distribution. Okay, the QI is 2.44, which is the 10th percentile for normal distribution of this. Okay, so 10th percentile of normal distribution 5 2 square. Okay, and for the next one, 0.3. Okay, so that is 3.95. So that is 30th percentile of a normal distribution of 5 2 square. Okay, so based on that, we can calculate the QI value. Okay, so we have QI value and also we have XI. So we plug XI versus QI. For example, the first dot is 3.01, 2.44. Okay, X1 is 3.01, Q1 is 2.44. Okay, it's here. 3.01 and 2.44. And so on, we can plot 3.35, 3.95. Okay, so we plot this and see if they follow a straight line. If we follow a straight line, then our guess probably is correct. Okay. And we can also plot as in the figure on the right. This is XI. This is the p-value, the probability for X less than certain value. Okay, same idea for these data points. For example, here, this is 3.01, 10%. Okay, the second one is 3.35, 30%. Okay, and so on. And the third one is 4.95, 50th percentile. Okay, again, if the dots close to the line, okay, then our guess is correct. So that's what is called probability plots. All right, so here is the last slides for section 4.10. Here shows two probability plots. So some on the right, on the left, okay, coming from population that is not close to normal. Why? Because the dots is not close to a straight line. Okay, the sample on the right, much better. Okay, even though it's not perfectly follow the straight line, but it's much better than the first case. Okay, so in the second case, we can see follow a normal distribution. Okay. And then what we left for chapter 4 is 4.11. It's called central limit theory. Okay, this is very important concept and also more complicated. So I want to save that for next week. Okay, so for today, let's just stop here.
Professor,